There is an animal in the ocean that fires water bullets that generate the temperature of the sun. It is not a shark. It is not a whale. It is not an octopus. It is a 4-centimeter shrimp that is nearly blind and lives in a hole in the sand. It sounds ridiculous until you understand what it does. When it closes its claw at 100 kilometers per hour, it creates a vacuum bubble that, upon collapse, reaches 4,800 degrees Celsius and 218 decibels. It generates plasma. It generates light. And it generates a shock wave that stuns, paralyzes, or kills everything nearby. During World War II, colonies of this shrimp produced so much noise that United States Navy submarines could not detect enemies using sonar. The loudest animal in the ocean is not the blue whale. It is a shrimp that fits on your pinky finger. Its name is Alpheus, but the world calls it the pistol shrimp. And everything about it defies what you think a shrimp should be. It is found in tropical and subtropical oceans around the world: the Mediterranean, the Caribbean, the Indo-Pacific, the Gulf of Mexico, the coast of Australia. Over 600 species have been documented, and all of them share the same weapon: a single, oversized claw that looks like a boxing glove, almost as large as the shrimp's entire body. The other claw is small, normal, used for feeding and grooming. But the big one is not a claw in any traditional sense. It is a biological firearm, a mechanism so powerful that engineers at some of the most advanced laboratories on the planet are now trying to copy it. The claw works like a gun. It has two parts: a socket and a plunger. When the shrimp opens the claw, water fills the socket. When it snaps the claw shut, the plunger drives forward and ejects the water through a narrow channel at speeds exceeding 100 kilometers per hour. At that velocity, the pressure in the surrounding water drops so dramatically that the water itself vaporizes. A tiny bubble of vacuum forms in the middle of the ocean. This is called cavitation. The bubble exists for less than a millisecond, but in that millisecond, something extraordinary happens. The pressure of the surrounding water crushes the bubble from all sides. As it collapses, the temperature inside the bubble spikes to 4,800 degrees Celsius. That is nearly as hot as the surface of the sun. The pressure inside the bubble at the moment of collapse exceeds 80 kilopascals. And for a fraction of a microsecond, the collapsing bubble emits a flash of light. Visible light, produced by a shrimp in the middle of the ocean. Scientists call this phenomenon sonoluminescence, a word that means light from sound. It is one of the least understood phenomena in physics, and it happens every single time a pistol shrimp snaps its claw. The shock wave from the bubble's collapse travels outward through the water at devastating speed. At 4 centimeters from the claw, the pressure is enough to kill a small fish instantly. At 10 centimeters, it stuns crabs, worms, and other shrimp into paralysis. The pistol shrimp does not chase its prey. It does not bite its prey. It shoots its prey with a collapsing star, and then it drags the stunned or dead animal back into its burrow to eat. The sound produced by this snap reaches 218 decibels underwater. To put that into perspective, a jet engine at full power produces approximately 140 decibels. A gunshot produces around 160. The pistol shrimp exceeds both. It is the loudest biological sound in the ocean. Louder than a whale song, louder than a dolphin's echolocation click, louder than anything any living organism produces anywhere on Earth. And it comes from an animal you could lose between your fingers. But one pistol shrimp is loud. A colony of pistol shrimp is something else entirely. In tropical reefs, thousands of pistol shrimp live in close proximity, all snapping their claws simultaneously. The combined noise is a constant crackling roar that sounds like frying bacon amplified to industrial levels. This noise fills the ocean. It is one of the most pervasive sounds in tropical waters worldwide. And during World War II, it became a problem that nearly compromised Allied naval operations in the Pacific. United States Navy submarines operating in tropical waters began reporting mysterious interference with their sonar systems. The sonar, designed to detect the sound signatures of enemy vessels, was being overwhelmed by a persistent crackling noise that operators could not identify or filter out. Enemy submarines were passing undetected because the sonar could not distinguish their engine noise from the wall of snapping sounds filling the water. The Navy brought in researchers from the University of California Division of War Research to investigate. After months of study, they identified the source: pistol shrimp. Colonies of 4-centimeter crustaceans were generating so much acoustic noise that they were effectively jamming military sonar. A shrimp was interfering with a world war. The discovery had an unexpected consequence. If pistol shrimp could block sonar, submarines could hide among them. Allied submarine commanders began deliberately positioning their vessels near known pistol shrimp colonies to mask their acoustic signatures from enemy detection. A weapon of war countered by a shrimp. But the pistol shrimp story does not end with its weapon. It has a second life that is equally extraordinary. The pistol shrimp is nearly blind. Its eyes can detect light and shadow, but it cannot see predators approaching, cannot identify threats, cannot navigate the open reef with any confidence. For a 4-centimeter animal living in an ocean full of fish, octopuses, and eels that would eat it in a single bite, blindness should be a death sentence. It is not, because the pistol shrimp solved its blindness problem the same way it solves every problem: by forming an alliance. The partnership between the pistol shrimp and the goby fish is one of the most remarkable symbiotic relationships in the animal kingdom. The goby is a small fish with excellent vision and fast reflexes, but no ability to build shelter. The pistol shrimp is a master builder with no ability to see danger. Together, they form a unit that is greater than either alone. The shrimp excavates and maintains a burrow in the sand, a complex tunnel system that serves as home, shelter, and escape route. The goby stands guard at the entrance, watching for predators with eyes that miss nothing. The communication system between them is extraordinary. When the pistol shrimp leaves the burrow to forage or clear debris, it keeps one antenna in constant physical contact with the goby's body. The antenna rests on the goby's tail fin. If the goby sees a predator, it flicks its tail. The shrimp feels the flick through its antenna, and both animals instantly retreat into the burrow. The entire sequence, from visual detection to physical signal to dual retreat, takes less than a second. They have been doing this for millions of years. Over 130 species of goby and 20 species of pistol shrimp have been documented in these partnerships across the Indo-Pacific. Each pair is often species-specific. They find each other as juveniles and remain partners for life. A blind gunslinger and a sharp-eyed lookout sharing a home on the ocean floor. But there is one more chapter in the pistol shrimp story that may be the most important of all, and it has nothing to do with the ocean. In 2019, engineers at First Light Fusion, a company based at Oxford University in England, announced that they were using the pistol shrimp's cavitation mechanism as a model for achieving nuclear fusion. Fusion is the process that powers the sun. It requires extreme temperatures and extreme pressures applied to hydrogen atoms until they fuse together and release enormous amounts of energy. For decades, scientists have been trying to build machines that can replicate this process on Earth. Most approaches use massive magnetic fields or powerful lasers to compress fuel pads. First Light Fusion took a different approach. They asked a simple question. How does a 4-centimeter shrimp generate solar temperatures in cold ocean water? The answer was cavitation, the rapid collapse of a vacuum bubble under pressure. The same physics that allows the pistol shrimp to generate 4,800 degrees from a snap of its claw could, in theory, be scaled up to achieve the conditions necessary for nuclear fusion. The company designed a system that fires projectiles at fuel targets to create cavitation bubbles similar to those produced by the shrimp. When the bubbles collapse, they compress the fuel to fusion-relevant temperatures and pressures. In 2022, First Light Fusion achieved fusion using this method. They confirmed it with neutron detection. A technology inspired by a shrimp had achieved what billions of dollars of conventional research had been chasing for decades. Researchers at Texas A&M University have also built three-dimensional printed replicas of the pistol shrimp's claw mechanism. Their artificial claw generated plasma at temperatures exceeding 1,500 degrees Celsius. A mechanical copy of a shrimp's claw, producing plasma in a laboratory. The implications are extraordinary. If the cavitation process can be refined and scaled, it could lead to clean, unlimited energy. The same mechanism that a 4-centimeter crustacean uses to stun a passing worm could one day power cities. 4 centimeters, nearly blind, lives in a hole in the sand with a fish that tells it when to hide. And yet, this animal generates temperatures found on the surface of stars, produces the loudest sound any living creature can make, jammed military sonar during a world war, inspired a breakthrough in nuclear fusion research, and maintains one of the most sophisticated symbiotic partnerships in the animal kingdom. Every predator in the reef knows the sound of its snap. Every submarine commander in the Pacific learned to respect it. And every physicist working on fusion energy is studying it. The pistol shrimp does not look dangerous. It does not look important. It looks like something you would brush off your hand without thinking. But inside that 4-centimeter body is a mechanism that produces conditions found nowhere else on Earth, outside of a nuclear reactor or the center of a star. The entire ocean hears this animal. The entire ocean knows what that snap means. And the entire ocean stays out of its way. 4 centimeters. That is all it takes.